Okay, so now we're going to look at an example problem using the conservation of energy equation. And in this example problem, we're involving a spring. So it's a little more in depth than what we've seen before. But we have a spring involved, and that's going to add some complication, but it's not going to be overly difficult. So here's our problem. It starts off with we have Sonic the Hedgehog. He bounces off a spring that is compressed 1.65 meters. If the spring has a spring constant of 1,950 newtons per meter and Sonic has a mass of 45 kilograms, how high does Sonic bounce? So let's go ahead and start picking out our nodes, and we will go ahead and highlight some of these things. And so here we go. I want to go ahead and highlight that we have a spring that is compressed 1.65 meters. And so that comes down to its x. Let's change that. So its x equals 1.65 meters. And then we also have another piece of information here. It says it has a spring constant of 1,950 newtons per meter, and so that's going to be K equals 1,950 newtons per meter. And then the last thing that we have is his mass. So his mass is 45 kilograms. So mass equals 45 kilograms. And then it asks me, it says, how high does Sonic bounce? And so that's going to be his height, which is the question mark. So if I were to draw these on my picture down here, this location right here would be his compressed location, so that's 1.65 meters, or his compression distance, and then this distance would be his height. And so that's h. And so we want to know what h is. Now I'm going to look at my equation down here for my conservation of energy, and I'm going to start canceling stuff out, such as whenever he lands on this and right before it bounces him off, he has no initial velocity, so his initial kinetic energy is gone. He's also going to be at the lowest point that he can be, and so his initial height is 0, and so that's gone. When he reaches the peak of his jump, his velocity is actually 0, and we've seen that in previous chapters. So his final velocity is 0, so that goes away. We're looking for his height, and at this point the compression of the spring after he jumps off is 0, so that's also 0 right there. And so I'm only left with these two terms, the 1/2 kx initial squared and the mass times the acceleration of gravity times the final height. So whenever I write my equation out, it's just going to be 1/2 the spring constant k times my initial compression squared equals my mass times the acceleration of gravity times my final height. And what I'm looking for is my final height in this first instance. So whenever I look at this, I need to get my final height by itself. And so seeing how mass and gravity are both multiplied to my final height, I can actually just divide by both of them. And what I do to one side, I have to do to the other. Right? And then those cancel out, and I'm left with my final height. So now I just have to plug in my numbers. My k is 1,950. My x is 1.65. And that's squared, all over my mass, which is 45 times 9.81. And then now I'm going to give you a couple seconds to go ahead and type this into your calculator while I do it, and then we'll see if we come up with the same answer. So I take 1/2, times it by 1,950, times it by 1.65 squared, and then I divide by 45 and by 9.81. And so I have my answer. What is your answer? My answer in this case is going to be 6.01 meters. So he bounces 6.01 meters, or roughly over 18 feet. Okay, so the next one says, or the next question says, how fast is Sonic moving right as he leaves the spring? So if I were to pinpoint that location, it would be right here, right? In this location right here, where his velocity is what I'm looking for. And so in this case, I'm looking for velocity, and it's going to be his final velocity after his spring pushes him off. So let me grab the eraser here, and let's go ahead and reset our equation down here. All right. Now in this instance, once again, he doesn't have any initial velocity whenever the spring is compressed, and he has no height. So this side stays the same. On this side, though, well, he actually has a final velocity, but the spring isn't compressed, and he has zero height. So my resulting equation that I'm going to use is going to be these two terms right here. And now it's just a matter of solving for my final velocity. So let's do that. Maintain this pink color so we keep it separate. I have 1/2, it's not pink, 1/2 kx initial squared equals 1/2 mv final squared. Now we can look at this and we see that we have 1/2 m on this side, and it's multiplied by v, so I can just divide both sides by 1/2 m. And these halves will cancel, and my m's will cancel, and just so on this side, the halves will also cancel. Now I'm still left with this squared, and so the only way I can get rid of the square is if I square root both sides, and so I'll go ahead and do that, and that will cancel that square. So my resulting equation is going to be the square root of k x squared divided by m equals v final. Now let's just plug in our numbers and work them out. The square root, k is 1,950. My x squared is 1.65 squared, all over my mass, which is 45. So now it's just a matter of plugging this into my calculator. You go ahead and do it while I'm doing it. Okay, and I came up with the answer of 10.9 meters per second. And so there are my two answers for this equation, and this is how we use the conservation of energy equation involving a spring.